Okay, so directional derivatives and a gradient vector. So first, let me just start with the directional derivatives. Okay, so directional derivative is actually, it's a type of derivative that has a direction. Okay, so we have let's say recall the very first few terms in the chapter 14. You have this z equal a function of x and y, and then you have the partial of x, and it has definitions of so partial of x in some point is defined as a limit. Okay, and partial of y, the difference is just the x-axis and the y-axis. Okay, now you have this. Okay, this is represent rate of change of z in x and y direction. And we can say the directions is based on unit vectors. I and j, the basis vector. So if you have if this is the unit vector, let's say this is A and B, and this is the point, the initial point. Now you have the unit vector A, B. Now, when we are dealing with this, which means your derivatives will have directions based on the vector, the unit vector A and B. Okay. Now I think it's better if we look at the picture. Let me just go into the next page. Okay, if we look here, this is what we have. Okay. So if the point P here is coordinate that is on the surface, okay, so the blue color here is our surface, and we have point P here, and we have the T, the tangent line there, and we have if you project this point into the xy plane, we have this, right? And let's say we are having another point Q here, and let's project this P and Q into our xy plane. Okay. Now we will have, okay, we will have, this is the vector, the unit vector. If it is having a scalar value h, then the component of x and y of the vector, it's having ha and hb. Okay. In which, if we are going to take approach of the limit, then we are going to include this HA and HB on X and Y. Okay. So we are having this is the projection, the P prime and Q prime. So let's say we have the vector is, or we can say it's component of this A and B. And we can have these relations. So between the X and X0, we will have an additional HA based on the unit vector. And we have additional HB for the y-axis. Okay. So we can have additional H. Okay, and then we can take the the difference in z, or z minus z0 over h, and this should be equal so this is having plus HA, this is plus HB, and then minus the initial point and divide by h. Now, if we take limit as h approaching 0, we got a rate of change of z, right, in direction of vector u. And this is called directional derivative. Okay. Okay. Now we can take this into our theorem, or our definition first. So directional derivative of f, okay, at some point in the direction of a unit vector. That's u is, we are going to have a new terms. This is how we are going to write directional derivative. So you have d and then u. U is basically based on the unit vector, but usually unit vector is all with u. So duf, so directional derivative in direction of vector unit vector u, okay, of a function f. Okay, so it's equal limit. This is basically of what we have right before. Okay. This is the definitions. And oh, if the limit exists, sorry. If the limit exists. And then what's the relation with the partial? We can have another theorem and also proof, but I think I will skip the proof parts. Okay, let's go to the next one. So the theorem is if f is differentiable function of x and y, f then f has directional derivative in the direction of unit vector. And we can write and we can split the unit vector each with each axis. So partial x and partial y. Okay. If the unit vector, this is the theorem, okay, the theorem. But let me add some notes, okay? If the unit vector u makes an angle theta with positive x-axis, then we can write this. Okay, it's just in a change to polar, okay, because it's a unit vector, so the radius should be one unit. Okay. Let me take some, maybe just one example, and then we can go to the next section. Find directional derivative at this point for the function. So we have three variables now. Okay, now we have three variables. Okay, so basically three variables are similar case, which you need just to add. Okay, so if you have 3 points like this, okay, instead of 2 points, then you need to just to use, it's basically the same limit definitions, but just adding the other variables. And you have A, B, and C. Okay. But of course, the more variables you have, the more difficult it's to be visually drawn. Okay. If limit x is. Okay, so based on what we have in these questions, first we need to have just casually calculate the partial, all the partial x, partial y, and partial z, right? So we can take a look at these equations. So we differentiate with respect to x. So we have 2x, y, and other will be a constant and 0. Partial of y, it will be x squared minus c cubed, another will be 0. And partial z will be negative 3 yz squared and plus 1. And plug in the point. This will be -4. This will be 1. This will be 1, right? Because z is 0, so just plus 1. So we can write the directional derivative -4. And then, oh, I'm sorry. This should be having a direction. So the direction of u is to, the direction is based on factor a. Sorry, it's not complete questions. So you need to find the factor u. Okay, that is the factor u. So we can just calculate all with the factor, each factor. And we have this is -3. So what does it mean is from this terms negative. So f is, or the function will be decreased 3 unit whenever the function f is going to direction of the vector. This is the vector, let's say the factor a. Okay. So whenever the function is going to the directions of a, the functions will decrease 3 units. Okay. The unit vector here. Okay. Yeah, unit vector is the same, similar with the chapter 12. Okay. I hope you still remember. So I think in chapter 14, you need to be familiarized with the chapter 12, chapter 13. Okay. So without giving any like what will be the final exam topics, if I say 14 and 15, of course it will also include 12 and 13 because it is implicitly included in chapter 14 and 15. So um, from 12, 13, 14, 15, all will be included. Okay, so 12 and of especially 12 and 13 is relatively close to chapter 14. Okay. 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 Any questions? Any questions? Sorry, this is should be having this information for the questions, having the direction in direction of factor A, and this is the factor A. Okay. All right. The next thing is actually the terms. It is called the gradient vector. Okay, the gradient vector. I think I need to just skip this, and Okay, the gradient vector. Let me just write our directional derivative formula with the partial. This is a, and then partial y, and then b. This is with the unit vector of a and b, right? So we already have these relations. Let's break down our relations. Okay, so instead of having this partial together with the vector, let's split or separate them. So let's write this in terms of both are each partial and the vectors, the unit vectors. Okay, so we can take this. This is the dot product, right? So with the dot product, you will get basically multiplication and addition, in which you will get the scalar result, right? And this part here, the partial part here, this is called gradient vector. And we are usually write this as I think in physics you have more likely to have this gradient vector. Okay, what's the definitions? Okay, if f is a function of x and y, then the gradient vector is defined as or we can say simply this is the vector. Each is a partial x and partial y. Of course, if you have more, you can have 3 variables, for instance. So I'm skipping some theorem and concept that is, I think, it's similar to the to what we have done before. So I hope you understand that. And let's say the U is A, B, C. F is differentiable. And we can show this and make it into 3 separate partial, x, y, and z. And from here, we can take the gradient to be or simply you can just write partial x, partial y, partial z. It's to look at in a more clear way. And the directional is just the okay. So same thing in the 3 variables. Also, they are looks similar. Okay. You can look the examples. Well, let me just write the example for you and see that if you understand how to use the directional derivative. Okay. If you have any questions, you can just type your chat box. Okay. So example, if you have the function of 3 variables, find gradient vector of f and find directional derivative at this point in direction now is v. Let me note this as a vector. Of course, if you read, it has I, j, k. It's a vector. Okay. Okay. Now, what we are going to do first, we are just make the partial, right? We can make the partial, or let me just write directly the gradient vector in terms of the partial. So partial of x, we just differentiate the function with respect to x. Partial of y, and partial of z. Right? And then this is at 1, 3, 0. So all 0, this is 0. It's 0, so it's 1, it's 1. And this will be 3, and it's 0. So 0, 0, 3, right? But I think the gradient factor itself is just this, the a. This is, we need this later. So next is the directional derivative at 1, 3, 0. And we have this vector first. We find the unit vector. It's 1 over square root of 6 because it's 1 plus, so it's square root of 6, right? Maybe make this in direction of, oh, I think this should be minus, sorry. So this is 0, 0, 3, and dot the unit vector. And this is 0, 0, and we just multiply the last part here. It's, if you multiply, it will be negative square root of 6 over 2. Okay. I hope at least you get the idea. Okay. So you have now directional derivative, and you have the gradient factor. And the directional derivative is actually gradient factor dot with the unit vector of the directions itself. Okay. Okay. Now another theorem about the how to maximize the directional derivative. So there's a theorem, and I think the theorem is not too complicated. Suppose you have a function that is differentiable. Let's say it's of 2 or 3 variables. And the maximum value of directional derivative, which means the slope, okay? If you want to imagine the directional derivative in visuals. So the maximum value of the directional derivative is and it occurs in direction of the gradient. So meaning the unit vector has same direction as the gradient vector. Okay, so the maximum value is this, and as a conclusion, the minimum value should be the negative of this absolute. And also if the gradient factor is 0, then the directional derivative is also 0 in all directions at point xy. Okay. I think for today, I think we can finish 14.6 and maybe a little bit going to 14.7. I think, but let's just see. Okay. Okay. Let's say we have example. Okay. You have these equations. This is the temperature. So you have this temperature equations. So temperature in space equations, which means space means you have 3 different coordinates, and this is in meter and temperatures in Celsius, of course. So when you are changing the coordinate, you are changing the temperature. Okay. Questions is in which direction? Does temperature increase fastest at this point? And when is the maximum rate increase? Okay, now before we are going to look at how we are solve the direction and the maximum rate, look at this equation first. This is simply, if you are just thinking as 1 over x, okay? If you differentiate this, what you get is the negative part, and then x squared, right? So we are going to do similarly, but in partials, because we have x, y, and also z, right? So first, to know the direction, we need to know the gradient factor, okay? So first, directions mean gradient, right? So gradient of temperature will be, let me just write partial x, partial y, partial z first, okay? And we do the partial derivative with respect to x, with respect to y, with respect to z. Okay, now we have x squared here. Based on the chain rule, it will be 2x, right? So we are giving negative first, giving 2x, and then multiply with 80. And divide. And then having all the terms, and then squared. And then the next part is with respect to y. Now we are having 4y. So we have negative 4y and 80. And then the same equation here, and then squared. And then with respect to z, it will be 6z. And this is our gradient here. Maybe we can simplify and make, I think we can take 160 out and the equations at the bottom. So we are left with the negative x and 2y and negative, it's 480,863,3z, right? So at 1, 1, and negative 2, you can try to look here. It's 2, 12, 2, 2, 4, 16, 16 squared. So I have 16 squared. So I have 10 over 16. So I have 5 over 8. Okay. And I have negative 1, negative 2, and 6, right? Or I can actually write in terms of negative I, negative 2j, negative 6k. Oh, positive, sorry. So this is the directions that we want to look for. So this, in this direction, increase fastest. Okay. At this point. Okay. Okay. The maximum rate, meaning we need to maximize the gradient vector. So what we are going to do, we just make it and takes the square root of 1 plus 4 plus 36. Or we can just write this 41 like that. So the maximum rate of increase is this. So whenever you have a functions and you are looking for directional derivative, you are looking for gradient factor, and when it's asking to maximize the directional derivative, meaning it's trying to maximize the rate, you can take the gradient factor and calculate the magnitude value of the vectors. Okay, so that is the maximum rate that the function can reach. Okay. Okay. If you have any questions, you can write in the chat box. The next sections is about the again, it's still similar the tangent plane, but it's tangent plane to level surfaces. So we are combine the gradient factor that we have learned now with the tangent plane that we have learned before, and combine in some in our relations. Okay. Let me check the. Okay, maybe here. Okay. Okay, this is the picture. I think. Yeah. Let me write the. This is tangent plane to level surface. It's still 14.6 because it's still directional derivative and gradient factor. Okay. So first, let this S be. So let S is a surface. Okay, with equations. Okay, so we have a big F here. So the functions is equal a constant. So this, how to read this equations, actually this is a level surface of functions with three variables. Okay, now look here. We have the gradient factor at this point P. Okay, this gradient factor, and we have the tangent plane. Okay, and of course we have learned on this R prime the tangent line, right? With the parametric equation and so on. And let me write here, maybe here. So let the point P, let's say it's having some specific point x0, y0, and z0 on surface S. Okay, and C, okay, C is curve on the surface S that pass through, and the curve is actually the vector functions. Okay, so it's chapter 13, right? So let me write all the terms there, and let the point P, it corresponds to T0. Okay, so we can write that at point P is actually x0, y0, z0 is actually at T0. Okay, now because C is on the surface, now we can write this in terms of, let's just write and combine all together the x, y, z, and with the parametric t is equal a constant k. Okay. And we differentiate with respect to t. Okay. So with respect to t, differentiate, and we can write if you want to write in terms of tree diagrams, you can also do that. Okay, and you can have this and this equal 0, right? Now, what we are looking here, we can separate this partial, become our gradient vector, and this becoming our r prime, right? So we can write this as we can also look from this proof that the gradient vector of f at point P is orthogonal to tangent vector, right? That passing P, or this is orthogonal. And as a conclusion, let me just erase this. As a conclusion, let me write here. Tangent plane to level surface is given by or you can write in terms of gradient vector at this point dot the r minus r0. Okay. And if you want to calculate the normal line, you can always do that also. We can make it in terms of parametric, or let me just write from the tangent plane. So we can write the normal line becomes this equal this equal this. This become the symmetric equations. Okay. Have you still remember? Okay, why it's becoming like this? The normal line is having the normal direction number, in which we get the normal direction number from here, right? Okay. Or if you want to include parametric, you can also include parametric if you want. But I think just this symmetric equation is just fine. Let me check. Yeah, I think mostly Yeah, mostly this is 14.6. There's some additional notes, but I think we'll add later. Okay, any questions? Okay, if not, what if, because this is all in terms of x, y, z, right? Let me give you another notes here. So what if the surface in form z equal function of x, y? What if the surface in form of this? How we can write the tangent plane? We can also write tangent plane, but first we need to define xyz like this, and then define this in terms of z, so minus z. Okay, so you have the gradient factor, so you will get partial x, partial y, but this is just -1. So what happens to the tangent plane? The tangent plane becomes you can use this just to solve. Okay, that's just special case. Maybe I'm going some little bit intro of 14.7. Okay, it's actually maximum and minimum value. So based on calculus 1, how do you know a point is minimum or maximum, right? This is the first thing that we need to define. Or you can say it's local minimum or maximum or absolute, right? We have the absolute one. But let's say we have just take just general maximum minimum, the local one. So we know the point if we know the critical point, right? The first is critical point when they have this first derivative equals 0, then you can find the critical point. But it's not always the case. You need to look for the equations and how long, like the interval, how long the interval is, and you need to check which one is having the maximum value and which one is having the minimum value. And also you can check with the second derivative test, right? The concavity, right? You can look how is your graph will look like. And of course, from the second derivative, you can also check the concavity, which whatever is concave up or down, and you will be able to tell whether the point will be in the maximum or a minimum range, right? But because now we are not only talking about two dimensions on the x and y, we have two variables, right? X, y. If we draw if it is three dimensions, imagine this three dimensions. Okay, so you may have like this, you have like going down like that, maybe like that, and you need to be able to tell which one is maximum, which one is minimum. Okay, so for example here, imagine if this is the highest one, this will be absolute maximum. Okay, the other one will be local max, and this will be absolute minimum, right? Okay, I think I will stop until here. And please wait on your Google Classroom. So if you want, you can open your Google Classroom and wait for some announcement. I've set the schedule maybe 1 or 2 minutes from now. Maybe in 1 minute or in 2 minutes, it will appear. So basically, we will have a small quiz. Okay, we will have a small quiz, and you have roughly around 15 minutes to fill in the form, and no need to submit the calculation paper. You only need to fill in the form, fill in the answers. Okay, let me check the. Okay, maybe around few seconds, or yeah, maybe around 1 minute. 1 minute left, and it will be posted on your Google Classroom. You can look at classwork under the chapter 14. Okay, can you see the announcement? Okay, can you see the form in the Google Classroom? If you can, no, really? Wait. Mm, yeah, wait for a little bit, a little bit. Okay. Okay. Mm, let's edit this. Okay, can you see now? Yeah. So you can open that, and you can try to work on the questions.